All right, so now what we're going to look at here is we're going to look at set operations in Venn diagrams. Venn diagrams are going to be a way that we represent a set and its operations, okay? And a set operation is going to be a way to combine and rearrange the elements of one or more sets. So the first thing that we need to get is this idea of a universe. So the universe is the set of all elements from which a set draws its elements. And this is very similar to a domain. So like, let's say, for example, I look at a set and I write it out inside of a set builder notation. And I say it's the set of all elements x belonging to z such that x equals 2k for k belonging to z. The universe for this set is going to be the set of all integers. So oftentimes when we write something in set builder notation, you can actually see right where it's coming from. Otherwise, we might actually have to be told what the universe is. So like, for example, I might be told that the universe, U, is equal to R, the set of all real numbers. Okay, so the universe equals R, and then I'm given this idea that B is going to equal the set 3 to 5. So what that means is that we're going to have the universe called all the real numbers, and then my set is going to be the set of real numbers from 3 to 5, not including 3, not including 5. And so consequently, we can think that 4 is in this set, 4.5 is in this set. Things like the square root of 11 will be in the set. The square root of 17 is going to be in the set. So every element between 3 and 5, not including 3 and 5, will be in this set, and they will all be real. On the other hand, we could actually rewrite this, and we could say U is equal to, let our universe equal to Z, okay? And we'll say that B is now equal to this set 3 to 5. But because the universe is Z, and because this is an open set, the open set from 3 to 5, there's only one element in there, and that's 4. So this one, B, is actually equal to just the single element 4. So you can see that that universe actually makes a big difference when we talk about sets. It's also going to end up making a difference when we talk about set operations, because we're going to have things like the complement of a set, and the complement of a set is really going to be dependent upon whether or not we are looking at, it's going to really depend upon what universe that we're looking at, okay? And so those are the first two things. We need to get, okay, one, we've got this definition of a set operation, and two, we've got the idea of a universe. So now let's look at a Venn diagram, okay? And the first one that we're going to look at, we're going to say, okay, well, a Venn diagram is going to be generally, we'll take for two sets, it's going to look something like that. We will draw them as circles, and then on the outside, okay, that would end up being the universe. So we might define the universe U as equal to Z, okay? And then let's define A. We'll call this the set A, this the set B. And the set A is going to equal 1, 2, 3, 4, 5. And the set B is going to be defined as the set of all x belonging to Z such that x is greater than or equal to -5 and less than or equal to 4. And so you can imagine what B is going to be. B is going to end up having, right, it's going to have -5, -3, -2, -1, 0, and the like. What we'll do first is we'll say, okay, well, in here, in this middle part, this is going to end up being called the intersection. Okay, so this middle part right there, and we'll color it blue. That's going to be our intersection. And inside of the intersection is going to be all the elements that these two sets have in common. So in this case, if we think about that, that's going to be 1, 2, 3, and 4. So 1, 2, 3, 4. We'll denote that, okay, we're going to call that the intersection. And the intersection is thus going to be A, and it'll be this upside down U, looks like a horseshoe, A intersects B, and that'll equal then the set 1, 2, 3, 4. And there we go. The next set that we're going to get is this thing here, and it's called the union. The next set operation is called the union, and it is going to be everything that is in both A and B. So we're going to use, this is called the union, and it's going to equal A union B. And let's put some information in here as well. So in A, but not in the intersection. So we'll put all the stuff that's in the intersection in the intersection. And then anything that's not in that intersection but's in A is going to be right there. That's going to be 5. Then for B, we're going to have everything that's not in the intersection. So in B, and in this region here, we have -5, -4, -3, -2, -1, and 0 inside of there as our sets. And this is then going to equal, so our A union B is going to be everything that's inside of this yellow set. And whenever we write our sets, we don't want to include any kind of overlap. Okay, so it's all that stuff that's inside of both of these. And so A union B is going to equal the set. Okay, and let's write this in set builder notation. X belonging to Z, such that X is greater than or equal to -5 and less than or equal to 5. And that ends up being the union. So those are our two basic operations, okay, that we're going to utilize here in order to talk about sets utilizing these Venn diagrams. Let's take a look at some other set operations. Our next set operation is called the complement. The complement is everything that's not actually in a set. Okay, so A complement, okay, is going to be all the stuff that we have here. We'll do this one again in blue. So it's going to be everything outside of A. So it's going to end up being everything outside of A. And that'll end up being a complement. Okay? So if we think about this from the perspective of what's actually in the set, this is the set of all X belonging to Z, such that X is strictly greater than or greater than 5 or less than 1. So actually, we'll use an or here. So X is less than 1 or X is greater than 5, since you can't actually be both of those. And that's a complement. And what we do is we utilize a bar. We might call it a bar as well. And so it's going to be everything outside of that area. Now, what we can do here is we can actually go in and we can use this. And one of the things that we can do here is we can take that off. And let's say, for example, I want to actually take the complement of A union B. So I'm going to take the complement of A union B. And so now that's going to be everything outside of A union B. And then we'll put that into pink. It's going to be all of this area in here. That's the complement of A union B. And so if you remember, A union B was all the numbers between -5 and 5. And so consequently, that would mean this would be the set of all X belonging to Z, such that X was less than -5 or X was greater than 5. And that would be A union B complement. And so this thing here, this is called the complement. The next two that we're going to look at are the difference and the symmetric difference. So the difference here is now going to be thought of as, say for example, B minus A. And this is the sign for difference. It's a subtraction sign. Makes sense. And what that's saying is it's all the things that are in B but are not in A. So what that would look like is all the things that are here that are highlighted in yellow. So it's all of that area right in there. And that ends up being B minus A. And so if you remember our sets, the set that we were using before, the ones that we had in common in here in the intersection were 1, 2, 3, 4. So this ends up being the set of all x, and why don't we just, we can write these all out. It'll be -5, -4, -3, -2, -1, and 0 from the set that we were using. And that'll be b minus a. Okay, so it ends up being all this stuff in here, -5, -4, -3, -2, -1, 0, if you take a look at the original one we did. A minus b is the symmetric difference, and you know, it's a little bit different when we work in sets. It's not just simply going to be the negative of b minus a. Okay? Instead, we know that this element, this is just going to end up being the element 5. That's the number there, 5. And so a minus b is just going to end up being 5. And so that's our idea of a difference. The difference is basically if you take the set B and you subtract everything that it has in common with A. Everything it has in common with A. So basically we're going to subtract out the... so another way for us to write that is going to be B minus A. And what you'll notice is that we're going to take B minus and we're going to subtract the intersection. B minus A intersect B. Okay? And that actually ends up being one of those relationships that we have there that might actually come in handy and is actually a little bit more explicit. Our final definition that we're going to look at right now is this thing called the symmetric difference. And the symmetric difference is given by, it's going to be A, and it'll have a plus sign with a circle around it, a plus sign with a circle around it, B. And we might also call it an XOR. This is actually, you're going to see that it's going to go along with, it'll go along with the exclusive OR that we see inside of logic. And what it's going to end up being is it's going to end up being A union B minus A intersect B. So it's basically going to be everything in A and everything in B that's not actually in its intersection. And so if we were to actually do this, and that would actually look like this. It's all the stuff that is yellowed here for A and B. Okay, so it's everything that's in the union, but not actually in the intersection. So here's A, here's B, and here's, remember this is 1, 2, 3, 4 from our previous one. And then we've got 5 here, that's just an A, and then -5, -4, -3, -2, -1 here. So that means that my symmetric difference is going to end up equaling the set -5, -4, -3, -2, -1, comma 5. And that ends up being my set using my symmetric difference. Okay? And there that is. Now, we've gone over, and what we've looked at is we've seen the union, the intersection, the complement, the difference, and the symmetric difference. These are going to be the 5 that we'll use on a regular basis. Okay, those are going to be the 5 most common ones. Now let's take a look at the logic that goes along with them. So what we're going to do now is we're going to look at each one of them, and we're going to kind of construct a table for all 5 of our set operations. So the first one is going to be our intersection. We'll write it A and this upside down U kind of thing, the horseshoe, intersect B. And what it's going to be in logic terms is it's going to say, oh, X is going to belong to A intersect B if, and we'll have these two things, these two requirements happen. X has to belong to A, and X belongs to B. So from a logic perspective, X will belong to the intersection of the sets if X belongs to both of the individual sets. X belongs to A and X belongs to B. Next up, we've got the union. The union will be A union B. That's got like a U. And X is going to belong to A union B if X belongs to A, and then this is going to be our inclusive or X belongs to B. If it is in one or the other or both, we end up getting the union. Next up is our complement. Call this A complement. X belongs to A complement implies that X does not belong to A. We can either use that, or we can put it as false that X belongs to A. Right? We can actually use the, if we kind of put a little bracket here, that would be X, not the case that X belongs to A. Next up, we have our difference. And that is A minus B. And so X is going to belong to A minus B. Implies that X belongs to A and X does not belong to B. Or again, you can utilize the negation. And then finally, our symmetric difference. We're going to get A, an exclusive or B. And so that's going to be that X belongs to A, symmetric difference B, implies that X belongs to A. And then we'll use the exclusive or, which ends up having the same symbol, X belongs to B. And so those actually give us an equated logic that goes along with the our set notation and our set operations, right? So basically, for those of you who are going to do more work with sets, okay, for those of you who are going to do more work with sets, what you'll do is you'll notice that anytime we want to prove that X belongs to the complement, we've got to show that X does not belong to A, right? That's how you show that X belongs to the complement. Or, if I want to show that X belongs to A union B, I end up showing that X belongs to A or X belongs to B, one or the other. We actually have to have one or the other happen. And so these logic representations end up giving us a way to prove that elements are in fact inside of our sets. So the next thing I want to look at now is these things called sequences of sets. Now, sequences of sets are very handy if what we want to do is we want to define sets in general, and we want to kind of give a very general definition for sets and build new sets utilizing new parameters. So how we'll do this, we'll start out, we'll have a notation. A is our set, and I is going to end up being an index. So AI is going to end up equaling, and what we're going to do is, let's say for example, we'll let X belong to the reals, and we're going to actually define it as the set of all intervals, X greater than or equal to negative I and less than or equal to I. And so that's going to be what our AI is. Now let's take a look at what that means. Now the set A1 is going to equal, well, it's going to go from -1 to 1, and it's going to be all the real numbers, so it's going to end up being the closed interval, -1 to 1. A2 is going to equal then, well, it's going to go, we're going to have, here's our index is 2, we're going to plug in 2 in for I, and so it's going to go from -2 to 2. So that one's gotten bigger, right? It's basically twice the size. It's going from -2 to 2. Okay, this one was the length of 2. This one here is now a length of 4. A3 then is going to equal -3 to 3. So you can see that's what we're doing is we're going to generate, in this case, using this definition. Now, not every sequence of sets has the same definitions. We'll look at another one. But each and every one of them in this particular sequence of sets is going to have this definition. Let's take a look at another one, just so that you don't think it's all going to look the same. So let's say B sub I, we now get, we're going to say it's going to be the X belonging to Z, okay, such that X is greater than or equal to -2I and less than or equal to 2I. So we'll just define it that way, and now we've got these I's. So now what we'll notice is that these are members of the integers. So if I take B1 is going to end up being, it's going to be a closed set. It's going to go from -2 to 2, but only integers. So in that case, it's going to end up being the set -2, -1, 0, and 1, 0, 1, and 2. Because it's going to include 1 and 2. B2, if we do this, it's going to equal -4 to 4, but again, everything's going to be an integer. Okay, so that's going to end up equaling -4, -3, -2, -1, 0, 1, 2, 3, and 4 finally. And so that's going to be the set. You can imagine B3 is going to go from -6 to 6, but only integers. All right? So what we've done is we've given a general definition for each one of these sets, call them BIs, right? And then we can generate lots and lots and lots and lots of sets. And the question is like, why does this matter? Why do we care? Well, one of the things that we can do is we can actually construct an intersection of all the AIs. Okay, so let's say, for example, I've got the intersection of all the AIs in this case, and we'll use this definition of AI. And notice I use the intersection, and what I'm going to do is I'm going to start just like a summation. I equals, and we'll start with 1, and we'll go up to 5. And I want to figure out what that intersection is. So if I think about this, what I'm going to have is, I'm going to have A4 is going to equal -4 to 4, and A5 is going to equal -5 to 5. Now, if you have to, pause the video for a moment and think about this for a second, because I'm, kind of, how are we going to like actually draw this? But you kind of think about it. If you think about it, -4 to 4 is in -5 to 5. It's like kind of like a Russian nesting doll. -5 to 5 is the bigger set. -4 to 4 is in there. -3 to 3 is in -4 to 4. -2 to 2 is in -3 to 3, and -1 to 1 is in -2 to 2. So if you kind of think about what we've got here, okay, is we've got a Venn diagram where we have a set of concentric sets. Okay, we've got A5, A4, A3, A2, and then finally A1 in the center. And the intersection of all of those is just going to end up being our A1. Just this guy right here. It's going to end up being A1. And so consequently, this intersection is just -1 to 1. Let's imagine something different. We could actually rewrite these in a different way. Let's say, for example, I want to know the intersection I equals 3 up to 5 of A sub I. Now we're only looking at from 3 to 5. So here's the smallest one, 3. Then we have 4, and we have 5. But that intersection is still going to look exactly the same. The difference, though, is that we don't have -1 to 1 or -2 to 2. -3 to 3 is the thing that's in all of them. So this ends up being -3 to 3. That's the basic idea here between the sequences of sets and operations on sequences of sets. Let's take a look at a union, and we'll use those B ones now. Let's say, for example, I want the union I equals 1 up to 5 of B sub I. Now that union I equals 1 up to 5 of B sub I is now going to be the union of all of those sets. So what you'll notice is that, again, this set of sets, from a Venn diagram perspective, here's B sub 5. Okay, it's going to go from -10 to 10. Okay, it's going to go from -10 to 10 because that's how we generate the sets. So we can go back here and look at it. That's how we're going to generate the sets. And then you'll notice that B sub 4 is going to go from -8 to 8. So it's going to actually be inside of B sub 5. And then we'll have a B sub 3, and B sub 2, and then a B sub 1. And so if we're thinking about the union is all the elements that are in one or the other of all the sets. So it's in fact going to be the entirety of this set, or just B sub 5. So it's going to end up being negative 10 to 10, because that's our definition, right? Which ends up equaling b sub 5. Notice now, if I take the union, I equals 3 up to 5 of b sub I still actually got the same situation. Now I don't have b3 or b2 or b1, but b sub 5 is still the outer shell. B sub 4 is within that. B sub 3 is within that one. And we're still looking at all of them all together. We'll make this one yellow. Well, what is that? That's still going to be the same exact thing. It's going to end up being equal to negative 10 to 10, which again is going to equal b sub 5. And that's the thinking about in terms of the unions. What do the unions look like? Okay. These ones, by the way, the examples that I gave you happen to be ones that are all kind of like one inside of the other, inside of the other, inside of the other. Okay. We can look at like another example that might actually give us, help us to think about what happens if they don't all look like, if they're not all nested, like those Russian nesting dolls. Now let's look at this set here. We've got C sub I equals the set of all x belonging to R, such that x is strictly greater than negative 1 over, and this should be I, negative 1 over I, and it's less than or equal to 1. Now, when I think about it from this perspective, what I want to get is, I just want to kind of think about what C sub I is. So like, for example, C sub 1 is going to end up being the set, now it's all in the real numbers, the open set negative 1 to 1, and we include 1. Okay? And C sub 2 is now going to equal the open set negative 1/2 to 1. C sub 3 is going to equal negative 1/3 to 1. And what you want to notice here is you want to notice that what will happen is that we will start to basically, we're getting smaller and smaller and smaller sets. That we go to negative 1, then negative 1/2, then negative 1/3. The next value is going to be negative 1/4, negative 1/5. Okay? And just for demonstration purposes, for those of you who've done some calculus, we know that what's going to happen is, as I gets really big, right? As I gets really, really large, what's going to happen is that negative 1 over I is going to start to approach 0. Okay? Negative 1 over I is going to start to approach 0. So what if I did something like this? This is the intersection of I equals 1, and we'll go up to infinity. I equals 1 up to infinity of C sub I. Now what we want to do is we want to say, well, what set of sets is going to be in every one of those sets? Well, one thing I know is I know it's going to end at 1. Because notice that we're going to go up to 1 in every single case. And the other thing is that we're going to go from 0 to 1 at least. Because each one of these values on the left-hand side, they're all negatives. Negative 1/2, negative 1/3, negative 1/4, negative 1/5. Well, what happens is, and again, this is just a little calculus. Don't worry about the calculus. It's just a demonstration. What we're going to get is that these values, as I becomes really large, what we'll end up getting is that these fractions end up becoming really small. They get really close to 0, and this intersection ends up becoming 0 to 1. It's a little mind bending. You want to think about it a little bit, but that's exactly what's going to happen. The intersection of all these sets is 0 to 1. And if you think to yourself, what set of elements can I guarantee are going to be in every one of these C sub i's? It's definitely that closed set, 0 to 1. Okay? Now, what about the union? Let's take the union I equals 1 up to infinity of our C sub i's. Now we're going to say, okay, well, what set do we get if we just actually take all of them? Well, here's the deal. These are a nesting doll. Okay? Once again, C sub 3 is in C sub 1. C sub 2 is in C sub 1. C sub 4 is in C sub 1. Okay? It's kind of cool like that we kind of notice, okay, so each one of the sets is getting smaller as I gets bigger, and so inevitably, the set that we get back when we union all of them is going to end up being negative 1 to 1. It's just going to end up being C1. And so that kind of gives us another way that we can utilize these sequences of sets by taking their infinite unions and their infinite intersections. Kind of it does some cool things. If you really get into the math a little bit more and you kind of start thinking very abstractly, you can get like really cool sets that you can take infinite sequences of and end up with totally unforeseen or kind of imaginative things. Okay? So this completes everything that we're going to be going over in terms of our basics on the set operations. So what have we done thus far? Just as kind of like a review. One, we took a look at the universe. The universe is the set of all objects that we are going to be pulling our sets from, kind of like our domain. We've got the intersection, we've got the union, our complement, the difference, the symmetric difference, and those are all of our set operations. Each one of them has a Venn diagram representation and also a logic representation. And then we have our sequences of sets. And our sequences of sets is a way to define general sets along an index I, or well, whatever index you want to use. We were utilizing I. All right, so this finishes up our discussion on set operations.